For our project, we decided to calculate the power output of a wind turbine. Before we begin with our calculations, let's first understand how a wind turbine operates. A wind turbine works in the opposite form of a fan. A wind turbine uses propellers, a spin shaft, and a generator in order to produce power. The wind causes the propellers to spin via kinetic energy, giving the propellers rotational and mechanical energy, which therefore causes the spin shaft to rotate. The spin shaft is then directly connected to the generator, which turns the rotational mechanical energy into electrical power. This clean form of energy is becoming much more popular in recent ages. Wind turbines offer a clean source of renewable energy. As of right now, the United States produces enough wind energy to power more than 18 million homes, and these numbers are drastically projected to increase in the next few years. Now that we have a little bit of a background on wind turbines, let's see our calculations.
The power produced by a wind turbine. And this is in an energy lens. So the first step is to find the energy of the density of the air, and that is just the kinetic energy divided by volume, because density is mass divided by volume. So you get 1/2 mass velocity squared divided by volume, which gives you 1/2 rho, which is density velocity squared. The next step is to find the energy captured, and that's just going to be your first step, the density times volume. So you're going to get 1/2 rho velocity squared times your volume, where your volume is length times area. The next step is to find the power, and your power is just energy divided by time. So in the second step, we found the energy. So you have the energy that you have from the first step just divided by time. And also, so right here you have length divided by time, and that is the definition of velocity. In our case, it's going to be meters divided by seconds, so that turns into another velocity. So you're going to have velocity cubed times acceleration, times area now. And the area is the area of the sweep length of the whole turbine. So you're going to have pi r squared. As you can see here, it's just all the area it covers. So yeah, then we have the Betz limit, which means that you have the wind energy coming in, but no turbine can capture all the energy. If it captured all the energy, there would be no wind coming out of it, which is impossible. So you always have wind coming out of the turbine, just like less so, because it captures some of the, or a lot of the energy of the wind. So the max limit it can capture is 59% of the wind energy.
So to find the power output of the wind turbine, we first start off with kinetic energy equals to 1/2 mv squared. And as you know, power is energy over time. So we plug back in 1/2 mv squared over time, and we find the mass of the air, mass of the gas is equal to volume times density. And the volume of the air is equal to the area times the height. And to find the height, we have to find the total length of the air going through, which is displacement, which is velocity times time. So then we have volume equals area times velocity times time, and we plug that into there. So we have the gas mass equals to area times velocity times time times density. Oh, and V is equal to wind speed in meters a second. So then you plug that back into the power of kinetic energy over time, and you get this right here, which as you can see there's 2 times. Those cancel out, giving us this equation. And to check if it's correct, we plug in the units. Area is meters squared, density is kilograms over meters cubed, velocity squared is meters a second cubed. And you cancel that out, you get meters squared kilograms over seconds cubed, which is the same as a watt, which is a unit of power. So then the area is pi r squared, which is 2025 pi. But now if we plugged all that into the equation, that would give you the theoretical, in a perfect scenario output. So we have to multiply that by the Betz multiplier, which is 0.37. So finding the area is, you plug that in, you plug in the density is 1.2 kilograms meters cubed, the velocity is 5 meters a second cubed, and the Betz limit is 0.37. You go all that and you cancel out the units, and you get a total of 100,076 watts, which is equal to 0.177 megawatts.